Welcome back for episode 3 of our educational series, Weather 101. Have you ever wondered why weather systems in Oklahoma and Arkansas usually move from west to east, or why, a lot of the time, hurricanes move from east to west across the Atlantic Ocean? Well, stay tuned to find out as we explore global circulation patterns. Before we learn about why Earth's atmosphere moves the way it does on a global scale, let's take a look at a satellite loop to actually see the atmosphere in action. This particular satellite loop shows water vapor in the upper levels of the atmosphere, around the height that a typical commercial airliner flies. Do you notice how the water vapor is moving from southwest to northeast across the central and eastern parts of the U.S.? And how about the pockets of higher water vapor moving east to west off the coast of Africa? This movement is actually quite usual, and let's find out why. We're going to play make-believe for a couple of minutes. What if the Earth didn't rotate, didn't tilt on its axis, and wasn't covered in water? If all of these things were true, the equator would always get the most direct sunlight, while the poles would always get the least. If you remember from episode 2 on the seasons, locations receiving the most sunlight, the most energy, tend to be warmer than those that receive less. Thus, the equator would always be warmer than the poles. You may have heard once or twice that warm air rises because it's less dense than cold air. This creates permanent low pressure at the surface near the equator because all the air molecules are leaving. They're going straight up. And high pressure at each of the poles. High in the atmosphere, the pressure patterns are reversed, with high pressure above the equator and low pressure above the poles. One thing about the atmosphere is that it's always striving to make things equal everywhere. To accomplish this, air molecules will move from high pressure areas, where there's already a lot of molecules, to low pressure areas, where there just aren't as many. The resulting global circulation pattern in this fictitious Earth is air moving from the poles to the equator at the surface, and from the equator to the poles aloft. The scenario we just talked about isn't reality. The Earth does rotate, leading something called the Coriolis force to bend airflow to the right. The Earth does tilt on its axis, which causes the sun angle at any one location to change throughout the year, resulting in unequal heating. And finally, the Earth does have a mix of land and water on its surface, leading to a non-uniform absorption of the sun's energy, since water absorbs more energy than the land does. When you combine the concepts from our make-believe scenario with the reality that we just described, you end up with 3 circulations instead of just one. The Hadley cell in the tropics, the Ferrel cell in the mid-latitudes, and the polar cell close to, you guessed it, the poles. The resulting airflow in these 3 circulations all give us east to west moving air in both the tropics and close to the poles, and west to east in the mid-latitudes, where we live. Remember the satellite loop we looked at to start this lesson? That it looked at the water vapor in the upper levels of the atmosphere where jets fly? Water vapor satellite is an excellent way to trace and evaluate areas of strong airflow aloft, areas that we call jet streams. Jet streams are important because they carry storm systems that lead to changes in the day-to-day weather at the surface. There are 2 main jet streams, the subtropical jet that forms where the Hadley and Ferrel cells meet, and the polar jet located between the Ferrel and the polar cells. Because the Earth tilts, the location of these jets changes throughout the year. For example, during the winter, the polar jet is found farther south, and in the summer, the subtropical jet shifts northward. Here are a couple of real weather maps showing wind speed and direction measurements of the jet stream taken by weather balloons. The map on the left occurred in the winter, while the one on the right is a summertime map. The blue and purple colors on the maps show areas where the wind speeds are the fastest. Let's look closely at the wintertime map, the one on the left. During the winter, the polar jet can dip southward, well into the continental United States. You'll notice that there's a lot more blue color and even some purple in this map. That's because the polar jet is usually faster than the subtropical jet is. When the polar jet plunges southward, very cold air does too. On this day, International Falls, Minnesota, where the red star is, saw a low temperature of 46 degrees below zero. The summertime map, the one on the right, shows the subtropical jet, an even warmer air northward into the United States. Fayetteville, Arkansas, again where the red star is, warmed to 100 degrees on the day these measurements were taken. Quiz time! Let's see how much you've learned about global circulations. First, pause the video, and then answer each of the 3 questions. Restart the video when you're finished. All right, here are the correct answers. If you chose C, 3 main global circulations in Earth's atmosphere, true, the polar jet stream is usually faster than the subtropical jet, and also completed the phrases polar easterlies, mid-latitude westerlies, and tropical easterlies, then you aced it. Thank you for checking out this episode on global circulation patterns in our Weather 101 series. Be on the lookout for episode 4 to learn more about fronts and air masses.